Finite automata, deterministic finite automata. We are going to discuss deterministic finite automata, lecture number 4. We discussed the basic concept in the previous lectures and rules for the deterministic finite. Now we are going to convert a regular expression to deterministic finite automata or simply finite automata, and how we are going to construct automata. These are the rules which must be followed. These are the rules which must be followed for constructing a deterministic finite automata. Means there is no null transaction. There must be a transaction for each input alphabet, one initial state, maybe a final, or maybe 0 1 or many final states, no substring, no substring transaction. And these are the rules which must be followed to construct a deterministic finite automata. The first example is a language which accepts all words. So the regular expression is a plus b whole square. So it accepts any type of words from a comma b, when the alphabet is a comma b. So the simple finite automata is 0 1 is q1 is the initial state plus the final state. So any combination of a comma b will leads the string in the final state, will leave the string in the final state. So this is the one way, and this is another way. The second regular expression and language is a language this start with a and it follow any combination of a comma b. The regular expression is a multiplied by a plus b whole square. So the word starting with a, so it start with a and follow by any combination of a. We are going to discuss it. We are going to draw. This is the final finite automata. So we are going to draw so that you can understand how the finite automata for this regular expression is constructed. The regular expression is a multiplied by a plus b whole square. So the language which start with a, then it is followed by any combination of substring beginning with a, beginning with a. So this is the language for this regular expression. Now we are going to construct a finite automata. So we start from q0. This is our initial state. Then the main condition in this language is that it must start with a. It means it must contain a single a. So for a, it goes to the final state q1. So for a, it goes to the final state. Then any combination of a comma b will lead the substring in the final state. So we apply this one. So it leads to the final state. We apply the second substring on a. It goes to the q1, which is the final state. Then any combination of a, any combination of a b. We apply the third one on a. It goes to the final state, and b, for a comma b we have a loop, b loop, a loop. So it still in the final state. Now we are going, this is our finite automata, but the rules say that on each state there must be a transition for each alphabet. So for Q1 we have only two alphabets a comma b. So on Q1 we have a transaction for a comma b for both alphabets, but in Q0 we have a transaction for Q1 for a1 for the first alphabet, but we do not have a transaction for the B. So we need to create a transaction for B. Where it is going to lead us? It is going to lead us to the dead end. It is going to lead us to the dead end. This is the dead state. So any alphabet, any substring which begin with B will go into the dead end. Then we need a transaction for each alphabet also in this state. So any combination of A comma B will lead us will lead us into the dead end. This is the complete finite automata for a language starting with A. The next one is the language starting regular expression of A plus B, the power of plus, mean a language containing any combination of A comma B, not including empty. So you need to construct a finite automata for that regular expression, and you have to submit it uh, uh, in the next class. The next example is a finite automata that accept no language. So if this type of questions arise, it means that you have to construct finite automata any type, but there will be no final state. There will be no final state. So the Q1 there is no final state, and also in this finite there is no final state. The second one is the regular expression of A plus B. It means that language contain only A and B. This is a regular expression is A plus B. It means it is a language where only two words are there, A and B. So we need to start with the initial state Q0, and on A it goes to the final state Q1. So on B it also goes to the, this is also a final state, it also goes to a final state Q2. So the basic condition is fulfilled. Now we need to complete the finite automata by following all the rules. Q0 contain transaction for A comma B. We have to input symbol A comma B. Transaction for A comma B is there, but for in Q1 there is no transaction for A comma B, and also on this. So we need to create a dead end because it only accept A comma B. If after that there is a combination of A comma B, it goes to a dead end. Also we need to create a transaction for each alphabet on Q2. So for Q2 it also leads any combination of A comma B to a dead end. So a dead end contain no transaction for any combination of A comma B, so to create a loop of A comma B. So we completed the deterministic finite automate. This is the complete deterministic finite automata which we created in the previous uh, slide. Now this is a language of words starting and ending with zero. So you need to create a finite automata. First you need to fulfill the basic condition. The basic condition is that the words starting with zero and ending with zero. So you need to create this one, the Q0 to Q1 on 0, Q0 to Q1 to Q2 also zero transaction. So a language containing finite automata will be like this: Q0 initial state, Q1, from Q0 to Q1 on input 0, and Q2 is the final state also on 0. So if a language, so on we are going to create a finite automata for a language which contains starting with 0 and ending with 0 comma 0 1 0 comma and so on 0. Sorry for this interference. So we are going to create a finite automata which accept a minimum of two zeros, starting with 0 and ending with 0. So we are in the final state. Then we are going to complete our finite automata if on q0, if a string which begin with 1, it lead us to a dead end, and there must be any combination of 0 1, so it lead us to a dead end. On q0, 0 and 1, for both input alphabet we have created transactions. Now in Q0 we have a transaction on Q0 but not on Q1. So Q1 must have transaction on 1. If we apply this substring, Q0 goes to Q1, 1 loop, 0 goes to the final state. Now if we have a substrings like 0 1 0 1 1 and 0, starting with 0 ending with 0, and 0 it goes from q0 to q1, 1 is a loop, then 0 goes to the final state, any combination of 1 it goes to the q0, q1 back to the q1, back to the q1, then any combination of 1 and 0. If there is another 0, if there is another 0, then we need a loop on q2. This is the complete finite automata for our language, and this is the complete finite automata for the language which we discuss. You need to study all these example on the slide. I'm going to share it with you, and then if you have any questions in these finite automata, so you have to ask to me.